Okay, this is a brief introduction to linear independence, which we will need um, to solve some differential equations of higher order eventually. So let's start with the basics, and I'll um, kind of explain linear independence and like why we end up needing it. So first off, what does that mean? So it means that we have two functions, in particular, the two solutions to a differential equation later. But linear independence is not exclusive to differential equations. So that's why the um, definition is somewhat generic. So it means that if we had two functions, y1 and y2, okay, they are not a constant multiple of each other. So what does that mean? I mean, we could look at that in a few different ways, but one way is that if we take some sort of constants, okay, C1 and C2, that we could combine these to get zero. All right, that's one way, that's one approach. Solving for either one really, but since C1 and C2 are constant, right? Like this is equivalent to saying, okay, let's move one of these to the other side. C1, Y1 equals negative C2, Y2. And really what I want to do is look at the ratio of y1 over y2. So I'm going to divide both sides by the y2 and divide both sides by the c1. But remember, these are both constant, so it's just some new constant, right, which we could call c. And therefore, if we take the ratio of these two functions and we get a constant, they are not linear independent. Okay. If it does not equal a constant, then they are linearly independent. Now, that's two functions, right? So sometimes with two functions, I mean, it's pretty easy. You can look at it by inspection. You know, sine over cosine that we have here is tangent, which is not a constant. Um, but more so, like, what if we start introducing a family of functions, like a third or beyond, right? Up to n number of functions. There's got to be a different way. So I'm not going to get into the proof in this video, but what we are looking at is it's called the Wronskian. May or may not have pronounced that correctly, but what that is you take all your functions and it's equivalent to finding the determinant of, so we need all the functions, but because we have n functions, right, we go down and we're starting with the original function. We go all the way down to the n minus 1 derivative. So the second row would be all of their derivatives, and then second derivative, okay, all the way down to the n minus 1 derivative. N minus 1 derivative of y1, the n minus 1 derivative of y2, and the n minus 1 derivative of yn, the nth function. Okay. If we can show that that is non-zero, then we could claim that all those functions are linearly independent, Li. All right. So I wanted to start, even though this first example, right, we could see, like I said, we could see the ratio is not going to be constant. I want to show how this Wronskian works. with something simpler. So the Wronskian of sine x and cosine x is equivalent to the determinant sine x cosine x in row 1, right? You just write the function y1, y2. And then the second row will be the derivatives. So here we'd have the derivative of sine is cosine, and the derivative of cosine is negative sine. And then the determinant for a 2 by 2 matrix, right? It's pretty easy, just multiply those two, subtract, multiply the other two, okay, the diagonals. So we would get negative sine squared minus cosine squared okay, negative cosine, and that is negative sine squared plus cosine squared, right, which we get negative 1, which is not 0. So therefore I know those two are linearly independent, even though we said it was prior to this. All right. Well, what if we add in a third function? I don't know, x squared, let's say. Okay, now the order in which you build the Wronskian, it really doesn't matter. But if you haven't seen a determinant of a 3 by 3, let's go ahead and look at that. So I'm going to rewrite this example below. So we have sine, cosine, and x squared, and what we're asking is, are these linearly independent? So to build the Wronskian, I'm just going to write w, it's of these three, right? We have sine, cosine, x squared. Then I already know these two from above. This is 2x, right? Determinant of x squared. Now the derivative of cosine, so we have second derivative of sine here, right, is negative sine, and the derivative of negative sine is negative cosine, and the derivative of 2x is 2. All right, we have our Wronskian built. Now to find the determinant. What you do is, the idea is you try to look for like either a row or a column with, in my opinion, the easiest, let's say call them a coefficient, okay? So like by inspection, I like this column here. So what does that mean? Well, another thing to keep in mind when you're doing determinants of any matrix is the signs here. So there's a pattern. You start with a plus, minus, plus, and then work your way through. But really, I just need to know this last column, right? So since x squared is plus, here we have minus, and then a plus. Okay. Again, I'm not really doing a lesson on determinants, but quick overview if you're rusty or if you haven't seen it before. And here's what these mean. So first I have positive x squared. All right, I'm just going to go ahead and write that here, positive x squared. And then we have a negative 2x. I'm going to leave myself a little room, negative 2x. And then I have a positive 2. Okay. Now, what you do is you cross out the row and column of that particular entry and you find the determinant of what is left. So what am I saying? I'm saying you cross, here's x squared, right? That row and that column out. Highlighter, so it's, yeah, anyways, that row and that column. And then the remaining 2 by 2, right, is right here. So I need to put that here. Okay, once you get some practice, you could really just do these in your head. But I'm going to go ahead and get rid of all those because we're going to need to think about the next rows here in a second, or the next remaining matrix. All right, so for that one, again, we had cosine, negative sine, negative sine, negative cosine. Okay, negative 2x. So that is part of this row. Oh, I wanted the highlighter. Part of this row and this column. All right, so what's remaining is sine, cosine, and then negative sine, negative cosine. Again, I'm going to undo that just so it's not so messy. So we have sine, cosine, and then negative sine, negative cosine. All right, now the last row and column, right, we'd cross out that and that. Okay, write the remaining 2 by 2, sine, cosine, cosine, negative sine. Well, now we have a bunch of 2 by 2s, so those determinants we could do because you just do the diagonals. If we were to call this A, B, C, D, it's AD minus BC. It's AD minus BC. So we have x squared, and then negative cosine squared, and then plus, well, actually, minus, right? Because we get AD minus BC, where BC is negative sine times negative sine, which is positive sine, but then we subtract them. All right, the next one, we would have sine times negative cosine, so negative sine cosine, minus negative sine cosine, so plus, which that particular one yields 0, plus 2, and here we have negative sine squared minus cosine squared. Okay, from above we know these negative sine squared and negative cosine squared is equivalent to negative 1. And this, of course, is 0. So we would have negative x squared minus 2, which is definitely not 0. Okay, so therefore those three are linearly independent. To wrap that up, why is that important? So there is a theorem in differential equations that says if you know solutions of a differential equation, then the combination of those solutions is also a solution if those functions are linearly independent. Okay, so what does that mean? That means if I had y1 is a solution, y2 is a solution, okay, they're both solutions to some differential equation, then a combination of these, okay, we don't know the particular, like we may need to find the constants, right? It might not be 1. But a combination of those is also a solution. Pen is being weird. Okay. If, again, these two are linearly independent. Okay, if those are linearly independent and they're solutions to some differential equation, then the combination of the two is also a solution.